Functions. What are they? Where do they go? What do they do? What can we do with them? Okay. A function is based on the first idea of a relation. A relation in math is a set of ordered pairs. That's that's what a relation is in our world. So an example of that, you'd have little curly braces, and you'd have an ordered pair: -2, 5. And I'm just making these up. They're not from anywhere. I just made up the ordered pairs. So the first ordered pair is -2, 5. The second ordered pair is 3, 4. The third ordered pair is 6, -7. And then 9, -8. Just I made those up. They didn't come from anywhere. They're not special. They just got picked at random. So that is a relation. A relation has a domain. It has a range. Okay. So another vocabulary word, domain. That is the set of all x values. And then we want to go numerical order. That's what I prefer. That also puts them on the coordinate plane. If you think about an ordered pair on the coordinate plane, if you put the x values in numerical order, that'll go from left to right. So when we're looking at the domain, we want to think left to right. Okay, so anytime you're thinking about domain, you're thinking, how's that thing move left to right? Where's it at left to right? That's what domain does. Okay, so for this particular set that we have there as an example, the domain of this set is going to be -2, 3, 6, and 9. Just the x values. That's all the domain is. It's just the x values. And then we have the range, which guess what it is? It's the set of all y values. And the way we want to think about that is bottom to top. The reason you want to think bottom to top is where are the lower y values? They're down at the bottom of the coordinate plane. The negative y values are down at the bottom. So you want to start at the bottom and go up for the range. Okay? Bottom to top. Domain is left to right. Range is bottom to top. It's the opposite way we read it. Okay? So bottom to top. Now, what's the range of our particular example? Well, it's the y values. I'm going to start at the lowest y value. Of the y values in that set up there, what's the lowest one? -8. So that's the first one I'm going to put. Then the next lowest, -7. Then the next lowest, 4 and 5. Has nothing to do with them being written in that order. Has everything to do with their value as far as y values go. Where they're at on the coordinate plane. Bottom to top. That's how you want to think about that. Now, that's just a relation. Nothing special about a relation unless it's a relation that can be called a function. Okay? So, special definition of a function. So this is what a function is. The title of the lesson was function. So this has got to be pretty important, right? It is a relation in which one value from the domain corresponds to one value from the range. functions do not repeat x values. It's okay if they repeat y values, but they cannot repeat x values. With my high school students, when we start talking about this, I talk to them. They're all starting to date, at the high school age, and they'll date the same person like 17 times within 2 months. You may be guilty of this too. I say two because I probably did that too. Thank goodness I'm over that. But if you want to function properly, don't repeat your exes. That's the way I teach them that, and they're like, "Oh my God, I should have never repeated my exes," and they remember that. Max, you don't remember that from you were in one of my classes, and I don't remember if we talked about that or not. I'm sure we did. But that's the way I remember it. If you want to function properly, don't repeat your exes. Functions don't repeat exes. You can repeat y values. It's okay to have the same feelings. Just don't repeat the x. Right? It usually they're an x for a reason. People are like, "Oh God, does he know me?" I don't. So, all right. So let's play a little game. Let's look at a relation and decide is it a function or not, and then tell its domain and range if it is. Okay. So, is the relation a function? If so, state the domain / range. We'll do both of those. Okay. So example A, and again, I'm going back to lettering my examples because I will ask you what letter are we on 17 times tonight. Maybe we won't have that many examples. 1, 6. There's our first ordered pair. 3, 5. There's our second ordered pair. -2, 4. There's our third ordered pair. 7, -6. There's our fourth ordered pair. And that's enough. We get the idea. Okay, so looking at that set of ordered pairs, that is a relation. Is that a special relation that we can call a function? Yes. Why? It doesn't repeat the x values. Yeah, x values don't repeat. We got a 1, a 3, a -2, and a 7. Definitely not the same number in the x position for any of those. So this is a function. So yes, it is a function. So you can write that if you want to. You can just write the word yes on there if you want to. Then the domain. And again, we want to go left to right with our domain. So what is the first x value in our domain? Going left to right. -2. 1, 3, and then 7. Yeah. That puts them in numerical order and left to right. Numerical order and left to right is the same. The range. That's a set of the y values from the relation. In this case, from the function. And they want to go bottom to top on that. So what is the bottom y value? -6. And then 4, 5, and 6, yeah. And somehow I subconsciously wrote them in reverse order there. Didn't realize I did that. But pretty easy when it's a set of ordered pairs. Really easy to look at and tell. Okay? They don't always write them as a set like that. Sometimes they will write them in a table. And I like the old-fashioned T-table. You put your x values on the left, your y values on the right, and you get, let's do like 4, -8, 3, -2, 6, -5, 4, -6. So there's a set of ordered pairs, not written in the curly braces and the parentheses, but just in a set, in a table like that. So is that particular relation, is it a function? Why not? Yeah, we got that repeating x value, so not a function. Repeated x value. And I'm just going to put in parentheses the 4, the one we saw there. Okay. Does it still have domain and range? Yeah, the instruction said if it's a function, write the domain and range. But understand that just because it's not a function doesn't mean it doesn't have a domain and range. It just domain and range of functions is really our focus here. So if it's not a function, I'm not going to worry about domain and range. It still has one. You just wouldn't write the 4 twice. You'd only write it once. Your domain would be 3, 4, and 6. Your range would be -8, -6, -5, -2. But since this is not a function, we're not doing that. But understand that it still does have that. So sometimes they write it as a list of ordered pairs. Sometimes they write it in a table like that. Another way that they might present it is what's called a mapping. And this is the one that's probably the least popular, but it's probably the easiest one. And they have these bubbles. And one is the domain bubble. And one is the range bubble. And they'll put some numbers in each of the bubbles. So let's do -6, 8, -4, 13. So those are my numbers. I just randomly picked those. And I'm going to pick some y values, -3, 10, 8. And then to create the ordered pairs in a mapping, what they do is they draw arrows to the corresponding value. So -6 goes to the 8. 8 goes to the -3. 4 also goes to the 8. 13 goes to the 10. And they'll have those arrows already drawn. You don't have to make that up. It's going to be there. And then you look at that and you say, okay, each arrow represents an ordered pair. This ordered pair from the -6 to the 8 is the ordered pair -6, 8. 8, -3. -4, 8. 13, 10. So we've got the ordered pairs. They're just in a different format. Same song, different verse. Maybe an old key change.
So if there's two ranges pointing to one domain and it's not a function?
Yes, that's the right idea. So here we have two. We have every x value or domain value is pointing to one single y value. It's okay, remember, to repeat the y values. It's not okay to repeat the x values. So in this case, it would be a function. The domain, put it in order. -6, -4, 8, 13. The range, put it in order. -3, 8, 10. Okay. So that one is a function. It doesn't repeat in the x values. As Jimmy said there, when you get a mapping with the domain and the range written there, let's say we had 3, 8, 9, -5, 18, -3, 1. And you drew your arrows. Let's say we had 3 going to the -5, 8 going to the -3, and 9 going to the 18, but 8 also went to the 1. In that case, not a function. Repeating x value. That 8 got used twice. It still has domain. It still has range. Else they couldn't write it in this bubble stuff here. But in our case, we're just looking for function, domain, and range, not necessarily all of those things. So we have a set of ordered pairs in a curly brace thing. We have a table. We have a mapping. The other ways that they can represent relations would be graphs. Okay, so we're going to sketch some graphs. You don't have to have graph paper for this. This is just sketching a rough sketch of a graph. So example E. Okay. I'm just going to draw a little coordinate plane, just a small one. Doesn't have to be really big. So there's me an x-axis and a y-axis. The quadrants, we talked about that last time we met, all those things. The graph of a relation could be just that blue line there. That's a graph of a relation. That blue line represents an infinite set of ordered pairs because it has x and y values that go on forever because it's got arrows on each end. Okay. Now, you may or may not remember this from way back, or maybe not as far back, but I don't know. Does anybody remember the vertical line test? The vertical line test is really how you can test if an x value is repeated, okay, on a graph. On a graph, the vertical line test says that if a vertical line can be placed anywhere on the graph, and intercept the graph in more than one place, then the graph is not a function. So what I tend to do is just like lay my pencil on there. I've got a big screen, so I've got a big pencil here. So if I lay that on there, how many times is that ruler running into that graph right now? One. So I'm gonna move it somewhere else. What about over here? What about here? Here. What if I extended that graph and went over here? It's still just once. So that line, that graph passes the vertical line test. So it is a function. What that means is everywhere I place that, you've got one x value and one y value that goes with it. So it doesn't repeat an x value. Okay? So this is a function. Okay? So
is a function just a way to know a straight line?
well, a straight line is a function if it doesn't fail the vertical line test. There are straight lines that will fail the vertical line test. Think about a vertical line. It would fail because it lands right on top of it the whole time. But a straight line is just an example of one of the graphs. We're going to see some more graphs that maybe are or aren't functions that we can test with the vertical line. The vertical line test is just anytime you have a graph, you can test it with a vertical line to see if it repeats x values and determine if it's a function or not from that. Okay, so this is a function. And here's where it gets fun, the domain. There's no way we could list every x value that graph has. Okay? So what we say is that the domain, it goes forever to the left, it goes forever to the right. That would be all real numbers. There's this thing called interval notation that uses the infinity symbols. Thank you, 2010s tattoo parlors, for bringing the infinity symbol back so that people know what they are now. Some of you may have one on you now. I don't know. But negative infinity to positive infinity, that means everything. That is the same thing as saying all real numbers. You will see it both ways throughout the course. So we're going to learn interval notation as we go. We're going to get better at it. I'm going to try to bounce back and forth between the two different notations because we need to be able to speak both of the languages, either the words, all real numbers, or an interval notation. It just means from negative infinity to positive infinity. There's no such thing and beyond, despite what was. You can't ever get to infinity. But, he thought you could. Bless his heart, he was a toy. The range, however, is also all real numbers. Because that graph goes forever up and down. So notice that the arrows go up. It's pointing to the right and up, but it's still going up forever. And as far as y direction goes, this is going down forever. Okay? So domain is all real numbers. So the range, in this case, because it's going forever up and forever down, is also all real numbers. And that would be from negative infinity to positive infinity. Now, let's look at another sketch of a graph that maybe isn't a function, because I think we learn more from the things that are not what we're looking for than we do probably the things that are what we're looking for. So we're on example F. So a little coordinate plane, doesn't have to be huge, just small, it's fine. And here is my graph. I'm going to draw this. Little sideways V there. A right angle action happening there. So if I test that with the vertical line test, how many times is that graph hitting my ruler?
Twice.
2 times right there. That is a repeated x value. I've got a y value up here and a y value down here. Same x value, 2 different y values. That's a no-no. We can't be a function and have that. That's how the vertical line test works. That when I place it on there and it hits it twice, hey, that's showing me it's got the same x value but different y values. So this fails the vertical line test. Not a function. Would anybody be able to tell me what the domain is for that? Because it has domain, it has range. What's the leftmost point as far as x's go?
0.
0. And then it goes to the right.
Infinity.
Infinities. 0 to infinity. The domain, if we were having to do that, it's good to kind of think about these things. So I'd have bracket 0 to infinity. You could also say all x's that are greater than or equal to 0. That's another way of saying that. Those two things say the same thing. So as we're learning about domain and range, we're going to learn kind of how to say it. Because we got to learn that kind of stuff as we go there. So it starts, the reason it's that is because it starts here at the y-axis. The x value right there is 0. And it goes to the right. So that's going toward positive infinity. Or all of these x values are bigger than 0. It's like there's 1 and 2 and 3 and so on forever. So that's all the x's that are greater than or equal to that 0. That's the reason the domain is that. Can anybody tell me the range?
Infinity. Zero.
Think about range going from bottom to top. Where's this one headed?
Infinity.
It's going that way up, down forever, right? Where's this top half headed? Up forever, right? So that's kind of like the line on the previous example. It's going down forever, it's going up forever. Doesn't matter that it's going to the left or right. We don't care when it comes to range. Range is up and down. So that's going forever. So that's going to be all real numbers. Or negative infinity to positive infinity. I like interval notation because it's shorter. It doesn't take as much writing. So all real numbers. And I don't have to spell words. I'm not, if you haven't noticed yet, I'm not real great at words. Okay. That's pretty cool. Let's do another. So a little coordinate plane, doesn't have to be real big. I'm gonna put this graph on there. And I'm gonna put a dot right there. And that point is 3, -4. That's what that ordered pair is. I'll zoom in there so you can see that a little bit better. You don't have to be perfect. Just kind of try to draw what I do. We're not looking for perfect graphs right now. If we want perfect graphs, we'll get the calculator out and have it graph an equation. We'll do that. Now, anybody remember what that's called? A parabola. Yeah, that's a quadratic equation. It's a parabola. It doesn't matter if you know that's what it's called or not. It's nice that we remember a few things. Now, vertical line test, because it's a graph. I can check a graph with a vertical line test. How many times is that graph touching my ruler? Once. What if I move over here? What if I move over here? Once. What about right here in the middle? Once. Right there, that point right there. Anybody remember what that point's called right there? The vertex. Yeah, that's right. Hey, that's good news. We're gonna be all right. Now, that passes the vertical line test. So this is a function. The domain, that it kind of gets slow about going to the right, but it still goes to the right. It kind of gets slow about going to the left, but it still goes to the left. Okay, so that graph is kind of just steadily getting wider and wider as you go up. Okay, so it's going forever to the left, forever to the right. So that's going to be all real numbers. Or from negative infinity to positive infinity. Now, this is the reason I put that point on there. Because what's the range? -4 is your lowest spot, right? That's your lowest y value. So it's all the y values that are what to -4? Greater than or equal to -4. In interval notation, that's going to be bracket -4 to infinity because it's going up. That's why we're going to the positive infinity. So our lowest point on the y part is -4, and then it's going up from there. So that's from -4 to infinity. Or you could say y is greater than or equal to -4. Those two things say the same thing about the range. Yes, sir.
Maybe a stupid question. Is there a reason that the greater than symbol has an underline?
Yes, because that means I'm including that point -4, the y value of -4. So the line is the equal to part. That means I'm including that y value as part of my range. So yeah, that is important. I'm glad you asked because I didn't even mention that. So yeah. Equal to mark on the inequality gets you a bracket, square bracket on the interval notation. So this is where the brackets and parentheses are not the same mathematically.
Are all the y values for the range not real numbers as well?
Yeah, well, they're not. There are real numbers, but they're only the real numbers that are greater than or equal to -4. The y value, they're real numbers, but they're only the real numbers that are above this spot. So we're not using all of these down here. -5 is not part of my range. -5 is a real number, but it's not part of my range. So we couldn't say that the range is all real numbers. It's only the real numbers that are greater than or equal to -4. It's only -4 to infinity. That part of the real numbers. So they are real numbers, just not all of them. There's a big difference in they're all real numbers and all real numbers. Okay. Let's do one more. One more picture. Coordinate plane. I'm zoomed in. That's why I'm drawing big. It's football time. So let's put that point at -3, 0. And that point at 4, 0. That point at 0, 2. That point at 0, -3. That kind of looks like a football, not really. Not a very good football. It'll work. Is that a function? No. You put the vertical line on that sucker, it's hitting it twice in all kinds of places. Where could I place it and it only hit it once, though?
On one of the points.
Yeah, on one of these endpoints down here, like at the tip of the football there. I could put it there and it only hits it once. But if I can place it anywhere and it hit more than once, it's not a function. So as long as I can place that vertical line up there and it hit it more than once, it fails the vertical line test. So this is not a function. Not a function. But it does have domain. Where do our x values go here? What's the lowest x value or the leftmost x value? -3. Where's the rightmost x value? +4. It goes from -3 to -4. You could also say that would be -3 is less than or equal to x is less than or equal to 4. That said, those are the mathematical symbols for saying the x values are between -3 and +4. That's what that's saying to us. The x values are between -3 and +4, including -3 and +4. What about the range? -3 to 2. So that would be -3 is less than or equal to y is less than or equal to 2. That's saying all of the y values that are between -3 and +2, including those two numbers. Biggest thing about these graphs is it a function or not? Okay, we're going to work on equations with domains in just a second. Biggest thing is being able to do vertical line test. Tell if it's a function or not. All right, so equations. Let's look at domain from equations. So same section, it's a different kind of topic here. Domain from equations of functions. The way that I like to teach this is I say that there are red flags for domain. There are only 2 of them. Okay. The first red flag. X's in the denominator of a fraction. The reason that is a red flag is because that can create division by 0. An example of that might be something like this, where you had like 3x over x minus 5. That's an example of a problem that would have a red flag because of the x minus 5 in the denominator. The 3x in the top has nothing to do with it. It's just part of the problem. The red flag comes from the x in the denominator. That's an example of a problem that has that red flag. Okay. The next red flag. That's a pretty crappy red flag. Oh, that's so much better. Color it. There we go. Red flag. Red flag number 2. It's the only other red flag. X's on the inside of a square root. Now, when the reason that is a red flag is because negative numbers create complex numbers in a square root. By complex numbers, I mean things that have the I, like a plus bi. That's a complex number. That I comes from the square root of -1. That's a definition thing. We'll get plenty of practice with that later on. It's not that important that you remember that. The thing you got to remember is that if there's a square root in the problem and there's an x inside of there, you've got a red flag. Okay, so in a function that might have that might be something like this: 3 square root of x plus 5 minus 8. The part that causes the red flag is the stuff under the square root. It has nothing to do with the 3 or the -8. Just the part on the inside. On the other one, the part that caused the red flag was the stuff in the bottom, the denominator of the fraction. Those are the only 2 red flags that we need to be concerned with right now. Later on when you get into Math 110, there's some other functions that we'll worry about. We'll talk about that then. Okay? These are the only 2 we got to worry about right now.
So what if we encounter?
You won't.
Oh,
Not in 100. Not in 100. We will get to those in 110, but you won't encounter any of those in 100. Okay? Now, those 2 red flags show up. What if the red flags don't show up? What if there's none? So that's our last little thing. If no red flags are in the function, then the domain is all real numbers. Or you could write it -infinity to +infinity. Or you could write that x is an element of the real numbers. That's the notation for that. So we're going to learn that as we go here. Okay. So if there's no red flags, then automatically all real numbers. Okay. If there's red flags, we got to deal with them. Okay, and I'm going to teach you how to deal with them. Okay. So let's get an example. I think we're on example I. And the instructions are: state the domain in set and interval notation. So this is where we start learning a little bit of notation stuff. Here is our function. F of x equals 3x plus 4. Very, very plain Jane problem. I don't know why Jane's got to be plain, could be plain Jane. Okay? But when I look at that, if I'm looking for domain, I'm looking for the red flags. I'm looking, is there a fraction with an x in the bottom? Is there a square root with an x inside? None of that's happening. So that tells me no red flags, no red flags. So I'm in my mind, I'm saying no red flags. So my domain set notation is this. Put a little curly brace. So this is a little bit more proper way of doing domain. All x's and then a straight up and down bar. So that means all the x's that are in this problem such that x is an element of the real numbers. That is set notation. It's set notation for the words all real numbers. Okay, that's what that means. X is an element of the reals, is set notation for all real numbers. It's a little shorter to write than writing out all real numbers anyway. Interval notation. Negative infinity to positive infinity. That's our interval notation. And that's what they want us to do. We're not doing anything else.
And again, how do we know the difference in to use a bracket or parentheses?
If you're including the numbers, if it's infinities, you're never going to use a bracket because you never can get to infinity because infinity's forever away. So infinities are never brackets. The brackets will only happen if you have a number that's included. And we'll see that in this, and I think it'll make more sense when we see an example that has it. It will, no doubt. The theory is never easy to understand, but the example is. So H-I-J, J comes after I, yeah. All right, so here we have f of x equals 5 over x plus 2. Okay? So again, it's asking me to state the domain of this in set and interval notation. So I'm looking for the red flags. So this one has which red flag? X in the bottom of a fraction, X in the denominator, that first red flag. So that right there, there's where my red flag exists, right there. So I'm just gonna put my red flag there beside it. Yeah, red flag. All right. Now, we can't ignore the red flag. We got to take care of it. So to find the domain, what we're going to do is we're going to find out what number do we need to cut out of this thing and remove it that's going to cause the problem. The problem that created by an x in the denominator, the problem that's going to be created by that is division by 0. So what we want to know is when is the bottom part equal to 0. So we set the denominator equal to 0 and solve. So in our case, we're taking x plus 2 equals 0. Whatever's in the bottom, the top part doesn't matter when it comes to domain, unless it has a square root. Okay? So when we have this red flag, we're taking whatever's down there in the bottom with the x stuff and setting it equal to 0 and solving that. So pretty quick solve on this one. All I got to do is subtract 2. X is equal to negative 2. That if x is equal to negative 2, that's the number that screws this up. Because if I put a negative 2 in there, what is negative 2 plus positive 2? 0. I cannot take this ruler and break it into 0 pieces. I've got one piece, or if I break it in half, I got 2 pieces. But I can't break it into 0 pieces. That's why you can't divide by 0. Okay? So x equals negative 2 is the number we need to get rid of. So the way we do that with our domain, in set notation, do the little curly brace, all x's, such that. That's how you're going to start your domain every time in set notation. Then you say, what can x not be? X cannot equal negative 2. It can be anything else, but it ain't negative 2. That's pretty simple in set notation. Yes, ma'am.
Are you always going to write the first x part?
Yes, yes, yeah. You will always write the curly brace, the x, and then the bar. Yeah. Now, in interval notation, the way that works is what you're going to do is you're going to tell what numbers are being used and jump over the negative 2. So the best way that I can explain this, I think, is with a number line. So I'm drawing a little number line. I'm going to put negative 2 in the middle. Okay? Out here is negative infinity. Up here is positive infinity. Okay? So I've got negative infinity on the left. All the numbers from negative infinity until I get to negative 2 work. I've got to skip negative 2. So the way I'm going to write that is I'm going to say negative infinity until I get to negative 2. And I'm going to put negative 2 right there. Not a bracket, because I'm not including the negative 2. I don't want to use it. So I'm going to use a parenthesis and then a U for union. So this is why we had to do the set stuff the first week, because we have to use some of those symbols. And then the negative 2 again, and then infinity. So let me explain what that says. It says, as you're coming along the number line, you're riding along here, everything's going great, there's a pothole. I got to dodge it. So I jump over the negative 2. That's what this little stuff in the middle is, me jumping over the negative 2. Parenthesis, union, parenthesis. That's how you skip a number. Okay? Parenthesis, union, parenthesis. That's how you skip a number. Say it again. Parenthesis, union, parenthesis. That's how you skip a number. Okay? After I jump over the negative 2, I'm landing right after it. I mean, right up against it. And then I'm going on forever again. I don't have any other numbers that cause me problems. The only problem I have is the negative 2. So I've got to skip it. You might remember on number lines having empty circles. Y'all remember doing empty circles on number lines way back? Elementary school, probably, maybe a little bit of high school. That empty circle is what we got to jump over. Okay, that's the pothole. The parenthesis, union, parentheses, how you're going to skip a number. That's the interval notation. Those two say the same things. The first one says all the x's as long as x is not negative 2. The second one says all the x's, but I'm going to skip negative 2. That's what it says. It takes practice. Interval notation it's different, and it takes a little practice. It's just going to take us some time to get better at it. You're going to see both of those throughout the course, so we're going to get better as we go. So don't panic right now if it's just overwhelming you. You're going to get better at it, okay? Let's do another one. What letter are we on? JK. Here's our function. G of x equals the square root of x minus 5 plus 8. Excuse me. So, what red flag do we have here? X under a square root. So, there's my red flag part. Okay. Now, how do I handle that? Well, what happens with a square root is if the numbers inside are negative, then it doesn't work. It becomes complex numbers, and we don't want complex numbers. We only want real numbers. So what we have to do is set the part under the square root greater than or equal to 0. Think about, can we take the square root of 0? Yeah, square root of 0 is 0. But if I said, what's the square root of negative 4? That gets a little bit tough, because negative 4 would be 2i. And that's that complex number stuff. So we want only numbers that are not negative. Okay? So we're going to take x minus 5 here and set it greater than or equal to 0. So it gives us an inequality to solve. How do I solve that inequality? Yeah, just like I do in an equation. I get x by itself, so I'm going to add 5. That's going to be x is greater than or equal to positive 5. So that means all the x's that are bigger than or equal to 5 So in my domain, in set notation, start it with the curly brace, get the bar, and then all I got to do is copy that inequality over. X is greater than or equal to 5. In interval notation, my lowest X value is 5. And it's everything bigger than that. So that's going to infinity. This is where the bracket comes in. Because it's got the equal to there. Abby, does that?
Yes.
That
That
makes a lot more sense than us trying to just talk about the theory of it.
Yeah.
Okay. So this is what guarantees us to not have a complex number or a negative underneath the radical or the square root. Okay. Set the whatever's under the square root. The 8 didn't matter. It was outside of the square root. Does not have anything to do with the domain. It's only that part. So we set that greater than or equal to 0, solved it, and then that becomes my set notation. My interval notation, okay, it's greater than or equal to, so that means I want to start at 5 and go up. So that's 5 to infinity. It's going to be a bracket there. Let's do some more. I think more examples. We see a few more of these. It starts to make a little bit more sense, or at least we start learning a process a little bit. And then maybe as we do the process a few times, it starts making sense what you got to do. Skylar, go ahead. Yes, absolutely. Both of them say the same things. This is set notation for writing the domain. This is interval notation for writing the domain. They're usually going to ask for one of them, not both of them. But I'm doing both on every one of these so that we see both of them. They do a little bit of all of it. Okay. Let's do another one here. Let's do example L. Let's throw this one at you. F of x, 6 over 2x plus 7. So what do we see here? Red flag. X in the denominator. So there's my red flag. Okay. Now, because it was an X in the denominator situation, how do I address that? What do I do with the 2x plus 7? Set it equal to 0. So the process is, if that's the red flag and it's an X in the denominator, you set it equal to 0 and solve it. So we're solving an equation here, which is more algebra than we've done in a while. Okay, so first step. How do I get x by itself here? Minus 7, yeah, good. 2x is equal to negative 7. All right, so dividing by 2, I'm going to end up with a fraction here, but that's okay. Not a big deal. I got x is negative 3. Oh, shoot, I almost did a decimal. That would have been, that's not what I normally do. So I'm going to leave it as a fraction, negative 7 over 2. That's how you're going to normally see it in 100. It's not as decimals, but as fractions. So that's why I'm going to leave it that way. Okay. Now, that tells me that that's the number I have to skip. Okay? So when I write my domain, the interval notation is the hard one. So I'm going to write the set one first. All x's as long as x does not equal negative 7 over 2. That's the easy one. You just make it a not equals and you got it. Put a slash through your equal sign. That's every x value except for negative 7 over 2. Interval notation for that, we're skipping negative 7 over 2. So I've got from negative infinity, then I find my skipping number, which is negative 7 over 2, parentheses, union, parentheses, and then I repeat the number I skipped. And there's the domain, written in two different ways. Once you get used to this and understanding that if I'm going to leave out, because this is not too big of a stretch to go from here to here, right? It's just not equals. What you got to get to connect together for you is that this thing up here is just that parentheses union parentheses. That's all that is. That means the same thing. Okay? It's kind of like learning new slang. It don't make sense until you know what it means. Okay? So once you get that connection and it clicks for you, it's going to go nice. Let's do another. Example M. This section definitely has more examples than the other two. Promise. This is the longest section of the night. So g of x is equal to the square root 6 minus 3x and then a minus 15 on the outside. So this one, the red flag is square root stuff. Okay? So we got that 6 minus 3x in the square root. That's my red flag. That's the issue. So my red flag for that tells me to do what with the 6 minus 3x? Not equal to 0. Greater than or equal to 0. That's where you set that inequality up. 6 minus 3x is greater than or equal to 0. What we're trying to do is make sure that the stuff underneath the square root is not negative. Greater than or equal to 0 is not negative. That's the reason we're doing that. Now, let's get x by itself in this inequality. What's the first step? Minus 6. So it's going to give me negative 3x greater than or equal to negative 6. Okay, so I've got to divide by a negative on an inequality. Does anybody remember anything special about that? What do you mean? Switch that, flip the symbol over, yeah. It becomes less than or equal to, and then you divide negative 6 divided by negative 3 is 2. You might know why you do that. My teacher always told me to. No. The reason is because when you divide by a negative, it changes the end of the number line that you're on. Because it swaps the sign. So number line, like think about my hand is where 0 is at. If I'm dealing with positives and I divide by a negative, a positive divided by a negative turns into a what? A negative. So that swapped me over to the other end. So I flipped around. That's why I flipped that symbol around. If I divide a negative by a negative, it flips me over to the positive side. That's why you flip that symbol. You may not ever do. I know I was never told. Just kind of had to figure that out. But that's what happens. If you just remember that process, that's the important part. If you divide by a negative or multiply by a negative to solve, you flip at the symbol. All right? And so that means all the x's have to be less than or equal to 2. So my domain in set notation.
I'm sorry, can I ask a question?
Yeah.
So when you flip the symbol, if the denominator is negative?
If what I divide by is negative. It doesn't matter what I divide into, it's what I divide by. So it's the number that's with the variable. That's the key thing. The number with the variable is negative, that's when you're going to flip the symbol. So what's our domain in set notation? Less than or equal to 2. Just copy that. So set it up solve it. Once you get it solved here, it's just copy that over. You don't change anything about it on the square root part. Interval notation for that. So you got to know how to read this. This says all the x's that are less than or equal to 2. So where are we starting? Negative infinity. And where are we stopping? 2. Is 2 included? Yes. Equal to mark. That's how we know it's included. So it's a bracket on there. This takes some practice. I mean, there's not much, those 2 rules are the only 2 rules you have to worry about right now. You got to and learn the process that goes with them. That's what it takes on that, is learning the process that goes with them. Let's do something a little easier for a second, and then maybe we'll finish this lesson with another one of those. So let's take a break from this for a second, and we'll come back to it, okay? Because I think it's getting a little heavy right now. Let's evaluate. Evaluate the function. That's easy enough. So here's our function. Example n, f of x is equal to 3x minus 9. And they want us to find f of negative 2. What does that mean to do? Plug in what? Negative 2 for x. So plug in for x. So that's going to be 3 times negative 2 minus 9. That's the same stuff we did in lab, isn't it? So that's negative 6 minus 9, which is negative 15. That's the answer we want right there. And we're not doing domain range. We're just plugging in an x value, getting a y value that goes with it. That's all we're doing right there. That's a little lighter than what we were doing. Example O. I always think the O kind of looks like a donut. So you put the patriotic sprinkles on the donuts. Does it not look like a donut when you put the sprinkles on it? Fat guy problems. Y'all don't even know. All right. All right. Here's our function, g of x. Let's do x squared minus 5x plus 8 over x minus 4. Don't freak out yet. We're not doing domain. We're just doing function value. We want to find g of 6. So what do we do with the 6? Everywhere there's an x, put a 6. And this is where the parentheses can help. I mean, it's still evaluating just like we were doing before. It's just in the function notation now. So everywhere there's an x, I'm going to put a 6. And I'm going to use parentheses because that's just the habit I started a long time ago that has done me pretty good for the last, we won't talk about how many years. And then we're just working that out. Whether you're working that with a calculator or by hand, it doesn't matter to me. I don't care. It's fine to use the calculator. No shame in your game there. So 6 squared is 36 minus 30 plus 8 over 2. 6 minus 4 is 2. 36 minus 30 is 6 plus 8 is 14. 14 divided by 2 is 7. So g of 6 is 7. That's what we found at the end. It's just taking a number and plugging it in. Okay. Here's our function. Remember, functions could be represented in a bunch of different ways, right? So here lately, we've been a lot of equations. It could be a set of ordered pairs. So my function is f. It's a bunch of ordered pairs. They want me to find f of 0 and f of 3. So this is where folks get they lose their mind because they're like, I don't have anywhere to plug an x in because I don't have an x. But you've got 4 x's up there. The x values in that function are -3, 0, 3, and 6. What x values do they want me to find the y value that goes with them? 0. What's the y value that goes with 0 as the x? 3. So this looks weird because it's not what we're used to doing, but it's actually easier. I don't have to do any math. I just go, 0 goes to f of 0 is going to be 3. Done. What's f of 3? -8. Done. I don't have, because that's the ordered pair. The x value is in the parentheses. The y value is what it's equal to. When we were doing that with the donut example, the x value was the 6, the y value was the 7. That's what we were finding. Okay. All right. Function value. Pretty easy thing. All right. Let's draw us a little graph here. So we're going to come back and we're going to do a domain and range or domain problem or two at the end of the night. But I'm going to draw a coordinate plane. I'm drawing it real wide and not very tall. Okay. I'm going to put a dot right there, and I'm going to put in parentheses the ordered pair -2, 6. And then I'm going to draw a line that kind of points down and to the left from that. Then I'm going to go over here, I'm going to put a dot right there, and I'm going to call that ordered pair 5, 6. And I'm going to draw a line going down and to the right from there. I'm going to attempt to connect those two dots with a straight line. I don't know that I can, but I'm going to try. I didn't bring a ruler with me that I could use this one though, couldn't I? Oh, well, that's good enough. We've drawn that picture, okay? In that picture, we have some intervals. We have what we call an increasing interval. We have a constant interval. And we have a decreasing interval. Okay. Now, if something is increasing, what direction is it going? Up. Okay? So that brings us to, okay, how do I read this graph? How do I read that graph? Left to right. So what part of that, as I'm reading it left to right, is going up? So that is starting down here and going up to there. So that's increasing, right? What's happening once I get to this dot? It's constant because it's flat, right? And then after I get to this dot, what happens here? Decreasing because it's going down and to the right. Okay? So now we got to figure out how to write that interval. So if this left side is your increasing interval, X values are what you want to talk about. Not Y values, just X values. What are the X values for that little piece right there? Negative infinity up to -2. Put parentheses on both of them. The reason you put a parenthesis on the -2 is because you don't know if that point right there is part of the increasing interval or part of the constant interval. It's the in between, right? It's the border. Okay, so you don't know if you're standing exactly on the border, like this line right here is the border between that side of the room and that side of the room. I'm about to fall, but you don't know which one you're on, so you can't count as part of that side. So we put a parenthesis. So what's the constant interval? Where does it start? At -2 and ends at 5. And then after that, we have a decreasing interval. Goes down and to the right. So it starts decreasing at what X value? 5. And decreases to infinity because it has that arrow going on the end there. Being able to look at a graph and tell if it's increasing, decreasing, or constant. Increasing, going up and to the right. Constant, flat. Decreasing, down and to the right. That's the only kind of 3 intervals that you can have. Looking at a graph and getting those pieces. Okay? That is section 2.3. That is the biggest one of the night, I promise you. Nothing any bigger than that one. That one's a lot of stuff. Do we need a break? Yeah, let's take a short break.